Welcome to Cloud Wizard. In this video we are doing a complete system design deep dive into Facebook, one of the most complex and heavily scaled social platforms ever built, serving over 3 billion monthly active users. We will cover the social graph, newsfeed ranking, photo storage, fan-out strategy, real-time notifications, and the full high-level and low-level design. Whether you are prepping for a meta interview or leveling up your system design skills, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video we are doing a complete system design deep dive into Facebook, one of the most complex and heavily scaled social platforms ever built. Facebook serves over 3 billion monthly active users, handles billions of newsfeed updates every day, stores hundreds of petabytes of photos and videos, runs a real-time notifications engine, and maintains one of the largest social graphs in existence. If you are preparing for a senior or staff-level system design interview at Meta, Google, Amazon, or any top-tier company, understanding how to design a social platform at this scale is absolutely essential. We will walk through the functional requirements, non-functional requirements, high-level system architecture, end-to-end user journey, core models and algorithms, low-level design, and the critical trade-offs you must articulate in an interview. Whether you are new to system design or polishing your final prep, let's get into it. Here is the core problem. Facebook is not a single product. It is a constellation of deeply interconnected systems. At the center is the social graph, billions of users connected by friendships, follows, group memberships, and event RSVPs. Every action a user takes, posting a status, uploading a photo, liking a post, joining a group, or RSVPing to an event, must be propagated through that graph to the right set of followers and friends in near real time. The news feed must rank hundreds of candidate posts in milliseconds using a machine learning ranking model, personalized for each of 3 billion people. Photos must be stored, transcoded, and served globally at low latency. Privacy controls must be enforced at every layer. And the entire system must sustain millions of writes per second and tens of millions of reads per second without downtime. Designing this requires thinking across distributed storage, real-time stream processing, graph traversal, content delivery, and ML-powered ranking simultaneously. Let's walk through the functional requirements. First, user identity and profiles. Users must be able to register, log in, manage profiles, and control privacy settings at a granular level. Second, the social graph. Users can send and accept friend requests, follow pages, join groups, and RSVP to events, creating a directed and undirected graph of relationships. Third, content creation. Users can create text posts, upload photos and videos, share links, create stories, and tag friends or locations. Fourth, the news feed. Each user sees a personalized, ranked feed of posts from their social graph, refreshed in near real time. Fifth, reactions, comments, and shares. Users can engage with content, and engagement counts must be consistent and fast. Sixth, notifications. Users receive real-time notifications for friend requests, reactions, comments, mentions, and event reminders. Seventh, search. Users can search for people, groups, pages, events, and posts. Eighth, groups and events. Users can create, manage, and participate in groups and events with their own feeds, member lists, and discussions. These 8 capabilities define the core product surface. Now the non-functional requirements. Scale is the defining constraint. 3 billion monthly active users, peak write throughput of millions of posts and reactions per second, and read throughput in the tens of millions of requests per second. The news feed must be generated in under 200 milliseconds. Photo upload and processing must complete within seconds. The social graph must support traversals across billions of nodes and trillions of edges with sub-millisecond lookups. The system must be globally distributed across dozens of data centers and points of presence, with active-active replication and regional failover. Availability must be 5 nines, less than 5 minutes of downtime per year. Consistency requirements vary by feature. Friend counts can be eventually consistent, but privacy checks must be strongly consistent. Data durability is non-negotiable for user content. The system must also comply with regional data residency regulations, including GDPR in Europe and LGPD in Brazil, which means data cannot leave certain regions without explicit consent. Here is the high-level system architecture. Requests from clients, web, iOS, Android flow through a global Anycast load balancer and API gateway layer that handles authentication, rate limiting, and routing. The core backend services are organized into domains. The user service manages profiles and identity. The graph service manages the social graph using a purpose-built graph store. The feed service handles news feed generation and caching. The media service manages photo and video upload, transcoding, and delivery. The notification service fans out real-time alerts. The search service indexes users, pages, groups, and content. And the groups and events service manages community features. These services communicate over an internal service mesh. All write events are published to a Kafka event bus, which drives asynchronous fan-out for feed updates, notification delivery, and analytics. Content is served from a global CDN for low-latency media delivery. A distributed cache layer using Memcached and Redis sits in front of every read-heavy service. The key metrics to memorize cold. Daily active users, which Facebook measures as the primary engagement signal. News feed generation latency. The P99 target is under 200 milliseconds. Photo upload success rate must be above 99.9%. Fan-out latency for a high follower post. How quickly does a post from a celebrity with 50 million followers appear in follower feeds? Notification delivery latency. Real-time notifications should arrive within 1 second. Graph edge lookup time. Sub-millisecond for direct friend checks used in privacy enforcement. Cache hit rate. The Memcached layer at Facebook historically sustains over 99% hit rate. CDN offload ratio. The fraction of media bytes served from edge cache rather than origin. These metrics are what a staff engineer at Facebook would be asked to define, monitor, and optimize during an on-call rotation. Let's trace the end-to-end user journey for a post going viral. A user with 5,000 friends opens the Facebook app. The feed service fetches candidate posts from the graph service, which returns the user's friend list and group memberships, and from a pre-computed candidate pool stored in a distributed cache. The ranking model scores each candidate post using signals like affinity, recency, engagement velocity, and content type, then returns the top-ranked posts. The user sees the feed within 200 milliseconds. She then creates a new photo post tagging 3 friends in a location. The post is written to the post store with a unique post ID. The media service receives the photo, stores the original in object storage, and enqueues transcoding jobs for multiple resolutions. A Kafka event is emitted. The fan-out service reads the event, fetches the user's friend list from the graph service, and writes the post ID into each friend's feed cache. Friends who are currently active see the post appear in real time. Notifications are dispatched to the 3 tagged friends. Within seconds, the post is live across the graph. The core models and algorithms. The social graph is stored in a purpose-built graph database. Meta uses TAO, a distributed, geographically replicated data store optimized for graph associations. Each node is a typed entity: user, page, group, event, or post. Each edge is a typed association. Friend like member, admin, attendee. Edge lookups are O1, by design using an association cache. The newsfeed ranking model is a multi-stage pipeline. First, candidate retrieval using lightweight signals to reduce thousands of candidates to hundreds. Second, a deep neural network scoring model that ranks candidates using hundreds of features. Third, heuristic re-ranking for diversity, content type balance, and policy compliance. Photo storage uses a custom object store. Meta's Haystack system stores billions of small image files as large needles in a haystack, avoiding file system overhead. For the notification system, fan-out on write is used for normal users, while fan-out on read is used for celebrity accounts with millions of followers to avoid write amplification. Groups and events use their own subgraph with membership edges and event attendance edges. Now the low-level design deep dive. The post store schema. Each post row contains post_ID as the partition key, user_ID, content_type, text_body, media_IDs as an array, privacy_level, created_, and a shard key derived from user_ID for horizontal partitioning. The graph store (TAO) stores associations in a two-tier architecture. An association cache tier backed by a MySQL persistence tier, with red replicas in each region. A friend-of-friend query is served entirely from cache. The feed cache. Each user has a feed slot in Memcake that stores a list of post IDs, pre-computed by the FAANG service. On read, the feed service hydrates post IDs into full post objects from the post store and CDN. The FAANG service uses a worker pool that consumes from Kafka and writes to Memcake. For users with over 100,000 followers, FAANG is deferred and computed lazily at read time. The hybrid FAANG strategy. The notification service uses WebSockets for real-time delivery and falls back to push notifications via APNs and FCM. Privacy enforcement is done at the API gateway layer and rechecked at the service layer using a capability-based access control model keyed on user_ID and privacy_level. Key takeaways for your interview. First, the social graph is the foundation of every feature. Always start by designing the graph store, the edge types, and how you will serve fast lookups at scale because everything else depends on it. Second, newsfeed is a multi-stage ranking pipeline. Not a simple query. Distinguish candidate retrieval from deep ranking and heuristic re-ranking. Third, FAANG strategy is the most critical scalability decision. FAANG on write gives low read latency but causes write amplification for celebrity accounts. So a hybrid model is essential at Facebook scale. Fourth, photos and media require a dedicated storage system. Do not use a general-purpose database for billions of small files. Discuss Haystack-style object stores and CDN tiering. Fifth, eventual consistency is acceptable for engagement counts and feed ordering, but privacy enforcement requires strong consistency. Always clarify consistency requirements per feature. If you can walk through the social graph, newsfeed pipeline, FAANG strategy, media storage, and privacy model with these 5 points clearly articulated, you will demonstrate staff-level system design thinking. That's a wrap on Design Facebook. If this helped you, please like, subscribe, and hit the bell. And I will see you in the next one at Cloud Wizard. And that's a wrap on Design Facebook. We covered the full picture. The social graph with TAO, newsfeed multi-stage ranking, hybrid FAANG for celebrity accounts, Haystack photo storage, real-time notifications, and the low-level design of the post store and feed cache. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.